Hey everyone, so as you might know, the new GPT-5 model has just been released and we thought we would pair that up following on the previous comparisons we did between Grok 4, Gemini and the O3 reasoning models in terms of how well it performs when we give it some modeling tasks, some complex 3D geometric modeling tasks. And if you recall from that video, which is what you currently see there, the Grok model, the latest Grok 4 model, didn't perform as well as we expected. Not bad by any stretch, but not super great. And then the OpenAI models were just, frankly, very disappointing and kept failing at all the tasks that we passed on to it. And then there was a bit of a dark horse, Gemini 2.5. Prior to this exercise, I never had high hopes for the Gemini models, but in our test, Gemini 2.5 proved to be the leading LLM in terms of these complex tasks, generating 3D models and calculating and applying wind loads. But GPT-5 has just been released yesterday, pretty much, and we thought we'd take it for a test drive. So what you're going to see here today is a much more complex model, so a more challenging task. This is the model we're looking at, this industrial type, portal frame type structure, the shed. And what we're going to do is we're going to use the vision tools in GPT-5 as well as the reasoning capabilities and get it to do a bunch of stuff that would otherwise be extremely time consuming. So you can see the settings that I set up there. You can see there it's the model from today or yesterday. Today is already the 8th in New Zealand, so that's yesterday. And we can see the various GPT-5 level models we've got there. We'll use the full one with the full capability. And what I'm going to do is I'm going to prime the LLM in GenFEA using DesignMate. I'm going to prime it with the model input so that it understands the model mathematically. But I'm also going to take a screenshot using the tool, and I'm going to rely on the computer vision of GPT-5 to understand the model. So first I'm just saying, look at the model, tell me if you kind of understand what's going on there. Look at the picture, look at the data, and give me some outputs. It's giving some info there. And then I said, okay, let's do a bit of a test. Let's say, what's the base spacing? And I don't give much more info. I just say, what's the base spacing? It's telling me it's 4.5 meters there. So let's go and check in the model. If we measure those 2 points, you can see at the bottom of the screen, yeah, it's 4.5. Then we tell it, okay, now adjust the base spacing to 5 meters. Again, not a lot of info, just saying, make it 5 meters. And you can see it's starting to output a table here for GenFEA. And we bring that into GenFEA. It didn't have enough token capacity to complete all of it, so I went on and said just continue from node 240. And I bring the nodes that it's already been generating into my model, because if the nodes are updated, then the elements attached to it will be updated. So we'll let it carry on. It did the remaining 20 odd nodes. So once that's done, we just click on OK, add it to the existing node sheet. So we can see it's all been imported there, all 260 of them. Off the face of it, it looks all right, but let's update the model and see and do some measurements and check whether those base spacings have now really been increased to 5 meters. So far it looks good. I can actually already tell just from the grid spacing there at 1 meter intersections that we've got 5 meter intervals there. So that is looking pretty good. And if we measure them, we can verify that it's 5 meters. So it's done a really good job, followed the instruction, maintained the connectivity of elements, and really kept its wits about updating this model and understanding what a base spacing is in context of this model using, you know, the vision tools and obviously the information that we provided in real time. All right, then I thought we've already used the Gemini model to calculate wind loads on this structure as well in another video that we did. And we were quite impressed with the results. But I thought, let's get GPT-5 to actually recalculate that. And we adjust the settings there a bit. We said we've got now 2 1 meter by 1 meter openings at the end bays on each side. So yeah, just go and recalc those and output those to us again. So you can see there we've got a location set up in this project somewhere in Australia, in Brisbane. So based on that, it should be enough information for it to determine the wind speed and the design requirements based on design standards without us having to tell it any of that. It should just be able to do that on its own. So we can see, all right, it's going through here. It's generating this huge table with lots of loads and all those elements. We bring it into the model. We replace the existing loads completely, and then we switch to that wind load X case, and we display the load symbol so we can actually see what it's done. And off the face of it, it looks pretty good. We can see the uplift on the purlins, and we can see the sideways force there in the X direction on the columns, and on the side rails there we can see uplift again. So we can see the direction of the loads appears to be correct. On the edges it's half of the internal ones, which makes sense. We can see the values there that is generated, so 4.54 in the middle and something like 2.97 or something like that, I think on the edges. And there's some values we can see for the uplift, and this is what it looks like on the other side. So we can see here we've got internal forces there acting on those members, which is what we expect to see. Now, this looks pretty good and I'm extremely impressed, but let's take it a step further and tell it to actually provide some calculations. We want to know how did it derive, to those values that it's actually applied. So what we'll do is we say, rather than outputting the calcs here, just give us a design pad script so we can plug it into design pad. And then verify and validate those calculations ourselves. And you can see it was a bit lazy. What it actually did is it took the existing loads as correct and it just scaled them. So if we look through these calcs here, you can see it's actually just scaled the existing loads from 4.5 meter base spacings to 5 meter base spacings, and it's kept some of them the same, and some of them it is then scaled according to the factor that it's determined there. So if we scroll down here, we can actually see that. So we had an old spacing, a new spacing, and then it took the original loads, summarized them, and then it calculated the scaled loads. Now, that's not wrong at all, but what I wanted to see is these loads were originally calculated by Gemini 2.5, and it did a really good job. But I wanted GPT-5 to actually recalculate those for us rather than just scale them. So even though this is correct, we're going to go back and we're going to say, okay, that's good, but recalc it. I want also to see the detailed calculations, and I want the code references attached to those calculations. So we go through the same process, generate the CalcPad calculation sheet, plug it in, and then we can look at it. And here we see, all right, so the correct standard has been assumed there. We can see the regional wind speeds and modifiers that it's used. We can see the pressure calculations there, factors that it's using, and how it's converting that back to tributary loads and applied loads, line loads and point loads on the model. So absolutely fantastic. I am blown away. I think we've got a new king. I am really happy to say that OpenAI is back in the lead after a short stint in second place, or even maybe third place, but definitely back in number one in our books, at least in terms of the stuff that we're using it for and what we're testing for. I hope you enjoyed that. Have a great day. Talk soon. Cheers.